Hi. So in this chapter we were examining digital systems. We have already explained these digital signals and systems in this frame. Now we will be examining this new frame here, logic circuits. So in this logic circuits, uh, we are going to deal with the fundamental elements first. There's a special name for them, gates. And then the other available gates in the market, we will be examining those gates as well. And finally, we are going to mention about combinational logic circuits, which is the connection of these gate elements somehow. There are some rules for this in this frame. So this video includes those three frames here. So let's start from the first one. Escape from here. And then open board. Open board. Bunu buradan yapmam lazım. Here we are. So that's the one. Here are. Let me clear this area first. And here are. So these are the gates that we are dealing with. We said basically there are three gates. One of them is called AND gate, the other one is the OR gate, and this is the NOT gate. So these words are the ones that we use daily communication. So there is a relation between these daily communication words and the logic gates. We will explain later on, not now. So as we have seen in circuit theory, we have some elements. We connect those elements together to make the electric circuits. In here, in digital systems, we've got elements, these AND gates, OR gates, and NOT gates. When we connect them together, we get a logic circuit or digital circuit. As we have seen in this circuit theory, there is a definition relation for each element. In here, there is a definition relation for those elements as well. So the inputs, so there are three elements here. The input is X and Y. The output is Z, which is included. So I'll write it down as a formula. That is Z is equal to X times Y. This OR gate is Z is equal X plus Y. And the last one is X prime. We show it X prime. So Z equals X prime. So that's the formula form of it. But in practice, since we know that digital elements have got digital signals and digital signals, that means digital input, digital output. So if you've got two inputs, the possible different inputs that you can apply to this element could be either 0, 0, or 0, 1, or 1, 0, or 1, 1. So if you've got two independent exput x, y, so these are the number of variables. Different inputs that you can apply with these variables is it could be 0, 0, 0, 1, 1, 0, or 1, 1. So these are the possible different inputs that you could apply. So the definition relation must show to us now what is the output for these inputs. So it is written here 0, 0, 0, 1. For this input 0, for this 0, for this 0, for this 1. Another way of saying this AND element, if at least one of the input variable has got 0 value, then the output is definitely 0. If both of them equal to 1, then the output is equal to 1. The second gate is called OR gate. So for these inputs, OR gate has got 2 inputs as well. So these are all the possible inputs. The outputs for these inputs are given here. And in other words, how we can explain this element, we can say that if both of the inputs are equal to 0, then the output is definitely 0. If any one of the input variables has got 1 value, then the output is equal to 1. That's the cases for in here the inputs, at least input has got 1 at least in order to get the output 1. The last one, although it is shown here, the 1 variable is enough to show that because the input is just 1. So the input to this element is this. So we are repeating those two. If they are different, so you could have written only the x0 and 1 value as the input. The output is the opposite of the input, isn't it? When it is 0 input, output is 1. When input is 1, the output is 0. So what I am saying here, we could make it like that. That is x, that is x prime output, 0, 1. The output could be 1, 0. So these are, we said, basic gates. Why we call them gate? Maybe we could explain those. Or assume that this y is equal to 0. One of the input is equal to 0. Y equal to 0 means this case, these two cases, isn't it? If you look at the output for this AND gate, when the y is equal to 0, is this too, isn't it? So that means when y equal to 0, whatever the x values are, you're going to observe 0, 0 at the output. That means x input is not effective on the z output. If you look at the other case, that means, let's say y is equal to 1 this case. So that means y equal to 1 is those two. For these inputs, my output is 0, 1. So I can say that that 0 is the same as x value, and that one in here, output 1, is the same as x1 here. So that means when the y value is equal to 1, what I am observing at the output, which is this z, is the same as x, isn't it? So that means when y equal to 1, I'm going to observe x at the output. Then we can make a conclusion out of this, saying that when y equal to 0, x does not pass through this gate. If y is equal to 1, then this y opens the gate, allow the x to come out of the gate or to go to outside the gate. So allow the x goes pass through. So that's why it is called gate. So we are controlling this gate by this y input, and according to that control, we are allowing the x pass through or do not pass through. That's why it is called a gate. There is a similarity there. Another thing that we need to explain here is in these definition relations there is no t. We know that t is the independent variable which represent time. So in these definitions we don't have time. So where is time then? So that is explained here. Make it a bit bigger. In here, when you look at this, you're going to see x and y, different inputs there are here. This is one of the input, 0, 0. So in this time interval, so this axis here is t. Why time comes in, I am trying to explain this. So if your input is 0, 0 for this time interval, and the second time interval, you've got input 1, 0. So this is time interval 1, that is time interval 2. Time interval 3 is 1, 1. Time interval 4 is 0, 1. Time interval 5 is 0, 0. So you are applying these inputs one by one after another, and you are allowed to repeat the same input anytime you like. If you make a sequence like that, it is called bit stream. This bit stream has got the time in it. So you are applying this first, and then this, and then this, and then this, and then this. So time comes in. So for these time intervals, you can write the outputs, because in this first time interval, this input does not change. So you're going to observe the same output for this time interval. So you can write the outputs for this bit stream. You can choose another bit stream, let's say includes only one bit stream. So you're going to observe only one output in the time interval between 0 and 5. So how we introduce the time is explained here. For the other gates, the outputs are shown here, so you can check whether it is true or not according to this definition relations that we used here in this table. So that is, let's come to this second slide. Clear this area once more. In the second one, we are going to see some new gates. So in the market, there are not only the fundamental gates that we just explained. There are some other gates are available in the market as well. These gates are NAND gates or NOR gates, XOR gates, and XNOR gates. So these are available as well. So, but this is very similar to the AND gate. For example, this NAND gate is the combination of an AND gate and an inverter. That means NOT gate. So that could be considered like that. That's an AND gate, and the output is connected to an inverter, a NOT gate, and put that in a box. You get that NAND gate. That's why, because of this NOT gate, there is a capital N in front of this AND gate. So it is called NAND gate. Similarly, we introduce NOR gate. XOR gate is different. So here is the XOR gate definition relation. That is the input. So these inputs are true for all these gates. So this is the third gate. This third gate, if the inputs are the same, that is the case of this and this. So in the first one, inputs has got same value, 0, 0. And in the second one, input values are the same, but that value is 1 in this case. Our output is 0, 0. So that means when the inputs are the same, XOR gate output is equal to 0. When they are different, that is the case, one of them is 0, the other one is 1. In here, one of them is 1, the other one is 0. XOR gate output is 1 1. So another explanation of XOR gate could be explained like that. When the output is equal to 0, that means input of the XOR gate has got different values, 0 1 1 0. If the output is 0, input of this XOR gate has got the same value. It could be 0 0 or 1 1. This one, XNOR gate, is the NOT form of this. That means you're going to, so this one is this XOR gate. That is XOR gate. Connected to an inverter. That becomes this gate, XNOR gate. That N comes from NOT, NOT OR. Another terminology, so we've got to explain here, this is called fan-in. Fan-in is the number of inputs of a gate, is called fan-in. So up to now we have seen fan-in 2 gates types here. There could be more than one input included gates as well. The highest one is 8, so 2 to the 8 number of inputs could be for a gate in the market available. So these are only 2 inputs gates. One more information for you. These gate elements are not available as a single one element. When you want to buy these elements, you're going to buy an integrated circuit which combines 2, 3 or 4 of these gates. For example, in here we've got a box here, that box called integrated circuit. Integrated circuit. So this is available in the market. When they sell you that integrated circuit, inside there are 4 AND gates, 2 input AND gates. So 4 of them, each one of them has got 2 inputs, so total 8 inputs terminals, and each AND gate has got a 1 output terminal. So altogether 12 terminals we've got here, but you see additional 2 terminals here. One of them is this, the other one is this. This one is VCC, the other one is ground. Inside, why we've got those 2 additional terminals, I will just explain to you. Inside these elements, these AND gates, there are transistors. You're going to see these elements in electronic courses. In transistor, the equivalent circuit of transistors has got dependent sources in it. And in order to run these transistors, in order to run this transistor in linear region, you've got to apply a DC source. That's why we've got these 2 terminals. And VCC is 5 volts and ground is 0 volt, of course. While this 5 and 0 is the representation, the symbols that we have seen here. 1 represents 5 volts, 0 represents 0 volt. So in digital circuit, 1 means in electrical case 5 volts and 0 for the 0 volt for the 0 symbol. So we will be using this information. So the total number of terminals that our integrated circuits have is 14. Ground and VCC is 2. 4 times 2 inputs, 4 times 1 outputs, the total numbers of 14. Here you are, that 14 seen here. The next step. Now what we've seen up to now, the gates we have seen. And now we came to a stage to define the logic circuits. It's called combinational logic circuits. If the gate elements are connected together, the circuit we end up with is called combinational logic circuits. So connection of the gates gives us combinational logic circuits. There are different type of elements apart from the gates which are called memory elements. When these memory elements are included, we use another sequential circuit, not combination, sequential logic circuits. But in the first part of the course, we will be using only the gates, so we will be dealing with combinational logic circuits. So we said we're going to connect gate elements to find out the logic circuit. But there are some rules for that. There are some allowed connections, some not allowed connections. The allowed connections are those. Any gate output could be connected to different gates inputs, as you see here. That is allowed, no problem here. But this connection here, in this figure, there are two not allowed cases. One of them is this. What it says is this: the output of the gate elements are not connected together and applied to another gate input. This is not allowed. In electrical sense, this is not allowed as well. Why is that? Assume that the output of this AND gate is 1, that means 5 volts, and this gate output is 0. So 1, 5 volts, and 0, 0 volts. So you're connecting 5 volt terminals to 0 volt terminals. That means you are short circuiting a source, isn't it? So this is not electrically done something, because when you connect those two, you cannot keep this voltage as equal to 1, isn't it? There's going to be a high current passing through, so you are in trouble. Therefore, this is not allowed because it is not possible electrically. For example, this electrically possible area here, why is that? Because whatever the current comes in is going to be divided to these lines, isn't it? So there's no problem here. The voltage of this node doesn't change, and current is divided to 3 different paths. So electrically there is no problem here. But on this side there is a problem. So this connection is not allowed. This is one restrictions on the connection in combination circuit. The other one is that feedback. Feedback is the output of any gate if it is connected to a previous gate input. Previous gate is means with backside gate here. So this is front gate, that is back gate. So the output of the front gate is connected to back gate input is not allowed. This is called feedback. So feedback is not allowed. That's the second not allowed case. Is not allowed in combination circuit. So if you do the connection of the gates according to these rules, that means allow these type of connections and not allow those two type of connections, then what you end up with is called a combination circuit. That is the example of this combination circuit here. Different type of elements. How many same type element you have used within this circuit is not important. The connections are important. This is allowed, this too is not allowed. So we end up with a combination logic circuit here. This logic circuit has got, in this case, 5 inputs and 1 output. So this is a combination logic circuit. If there is, apart from the gate elements, if there is memory elements, a different type of element in digital systems, then this circuit has got a special name. It is called sequential circuit. The second part of this course we will be examining this circuit as well. So it's going to be different from the previous one. So that is the end of this uh, videodan.